Close your eyes and imagine this. Buried beneath millions of years of rock and sediment lie the forgotten remnants of civilizations that mastered technology we can barely comprehend today. What if the Great Pyramid's impossible precision, the Antikythera mechanism's advanced gears, and Damascus steel's mysterious strength aren't anomalies of human ingenuity, but echoes of something far more profound? Scientists have discovered that after just 10 million years, virtually all traces of our modern world would vanish completely from the geological record, leaving future archaeologists no evidence we ever existed. If this is true for us, what about those who came before? Tonight, we'll journey through 4.6 billion years of Earth's hidden history, exploring the possibility that human civilization isn't our planet's first attempt at intelligence. From the Silurian Hypothesis to ancient megalithic mysteries, from mass extinctions that reset the evolutionary clock to industrial signatures that disappear like whispers in deep time, prepare to question everything you thought you knew about our place in the cosmos. As you drift into peaceful sleep, let your mind explore the tantalizing possibility that we are not alone in time, and that somewhere in Earth's vast geological memory, the shadows of previous civilizations await discovery. Welcome to the Sleep Lab, where science meets serenity, and every documentary is designed to guide you gently into the most restful sleep of your life. If you're ready to explore the universe's greatest mysteries while drifting off to peaceful dreams, hit that subscribe button and ring the notification bell so you never miss our latest journey into the unknown. Now, let's begin this incredible voyage through deep time together. Let's move to our first part of the documentary. Welcome to Chapter 1, where we'll explore the almost incomprehensible vastness of Earth's timeline and discover why the question of previous civilizations is far more complex than it first appears. To truly understand whether we might not be the first civilization on Earth, we must first grasp something that challenges the very limits of human comprehension: the sheer immensity of geological time. Picture yourself standing at the edge of the Grand Canyon, looking down into layers of rock that tell the story of millions of years. Each stripe of color represents entire epochs where countless generations of life lived, evolved, and passed away. Yet even this magnificent canyon only reveals a fraction of Earth's true age. Our planet has existed for 4.6 billion years, a number so vast that our minds struggle to contain it. To help us visualize this cosmic timeline, imagine compressing all of Earth's history into a single calendar year. On this cosmic calendar, Earth forms on January 1st as a molten ball of rock and metal, bombarded by asteroids and comets in a violent dance of planetary formation. The first primitive life appears sometime in February. Simple bacteria floating in ancient seas that bear no resemblance to any ocean we know today. These microscopic pioneers survive and multiply in an atmosphere that would be instantly lethal to us, rich in methane and ammonia, but containing virtually no oxygen. For months and months on our cosmic calendar, nothing but bacteria and other simple microorganisms inhabit our planet. Spring passes, then summer, then autumn, and still the most complex life forms are invisible to the naked eye. It isn't until November that we finally see the emergence of complex multicellular life. The first animals with shells and hard parts don't appear until November 20th. Dinosaurs, those mighty rulers of the Mesozoic era, don't arrive on the scene until December 12th, and they dominate the planet for just 2 weeks before a cosmic catastrophe erases them from existence on December 26th. And humanity? We appear in the final hour of December 31st. Our entire recorded history, from the first cities of Mesopotamia to the present moment, spans just the last few seconds before midnight. The entirety of human civilization, with all its achievements and struggles, occurs in less time than it takes to draw a single breath on this cosmic scale. When we consider this perspective, the idea that we might be Earth's first and only intelligent civilization begins to seem less like a certainty and more like a profound case of temporal arrogance. This temporal humility becomes even more important when we consider the work of astrophysicists Gavin Schmidt and Adam Frank, who in 2018 proposed what they called the Silurian Hypothesis. Named after an ancient reptilian species from the British science fiction series Doctor Who, this hypothesis asks a deceptively simple but revolutionary question. If an industrial civilization had existed on Earth millions of years ago, would we be able to detect it today? Their investigation into this question reveals just how ephemeral the traces of technological civilization truly are. Schmidt and Frank began by examining what kind of geological signature our current industrial civilization might leave behind. They looked at the dramatic changes we've made to Earth's atmosphere, pumping billions of tons of carbon dioxide into the air, and fundamentally altering the planet's climate. They considered our nuclear weapons testing, which has scattered radioactive isotopes across the globe in distinct patterns that future geologists might recognize. They examined our production of synthetic materials like plastics, concrete, and aluminum, substances that don't occur naturally and represent clear evidence of technological activity. What they discovered was both fascinating and sobering. Yes, our civilization would leave traces, but these traces would be detectable for a surprisingly short period in geological terms. After just a few million years, virtually all evidence of our industrial activity would become undetectable or indistinguishable from natural processes. The excess carbon dioxide in our atmosphere would be absorbed by natural processes, returning atmospheric composition to pre-industrial levels. Our nuclear isotopes would decay, their signatures fading below the background noise of natural radioactivity. Even our most persistent synthetic materials would break down or become so dispersed as to be unrecognizable. The physical structures we consider permanent would fare even worse. Our cities, built primarily of steel, concrete, and glass, would crumble within thousands of years once maintenance stopped. Steel rusts, concrete cracks and erodes, and glass shatters. Nature is remarkably efficient at reclaiming human-made landscapes. Consider how quickly vegetation reclaims abandoned buildings, how rivers change course and bury human settlements, how earthquakes and volcanic activity reshape entire regions. The magnificent pyramids of Egypt, built just 4,500 years ago, are already showing significant signs of erosion despite being constructed from some of the most durable materials available to ancient engineers. This realization leads us to a profound insight about the nature of geological preservation. The Earth is not a museum that carefully preserves everything that has ever existed on its surface. Instead, it's more like a constantly shuffling deck of cards, with tectonic activity, erosion, and sedimentation continuously mixing and rearranging the evidence of the past. Mountains rise and fall, ocean floors spread and subduct, and the very continents drift across the planet's surface like slow-moving ships. The process of fossilization itself reveals just how rare preservation truly is. Despite the billions of organisms that have lived and died on Earth, we have fossil evidence for less than 1% of all species that have ever existed. The conditions required for fossilization are extraordinarily specific: rapid burial, the right chemical environment, and millions of years without disturbance. Most organisms simply decompose completely, leaving no trace of their existence. If nature is this selective about preserving biological remains, how much more challenging would it be to preserve technological artifacts? Consider what paleontologists call the recency effect. The fossil record becomes increasingly sparse as we look further back in time, not necessarily because life was less abundant, but because older deposits have had more opportunities to be destroyed by geological processes. Rock layers are subjected to pressure, heat, and chemical alteration that can erase even the most durable traces of past life. Entire geological formations can be completely erased by erosion or metamorphism, taking with them any evidence they might have contained. This understanding transforms our perspective on the absence of evidence for previous civilizations. The famous phrase, "absence of evidence is not evidence of absence," becomes particularly relevant when we consider the geological timescale. Just because we haven't found clear evidence of pre-human industrial activity doesn't mean such activity never occurred. It might simply mean that the evidence has been erased by the same processes that will eventually erase most traces of our own civilization. Schmidt and Frank's work also highlights an important distinction between different types of geological signatures. Some markers of technological activity might persist longer than others. For example, certain isotopic ratios created by nuclear processes could potentially remain detectable for millions of years in the right circumstances. Similarly, unusual concentrations of rare earth elements or synthetic molecules might survive in specific geological contexts where they're protected from normal weathering processes. The search for such signatures requires us to think like cosmic archaeologists, looking not for intact artifacts, but for subtle chemical and isotopic anomalies that might indicate past technological activity. This is incredibly challenging work, requiring scientists to distinguish between signatures that could indicate technology and those that might result from natural processes. For instance, unusual concentrations of metals could indicate industrial activity, but they could also result from volcanic processes or asteroid impacts. The implications of the Silurian hypothesis extend far beyond Earth. If technological civilizations can effectively erase themselves from the geological record in just a few million years, this might help explain why we haven't found evidence of alien technology despite the vast age of the universe. Perhaps the cosmos is actually teeming with the remains of past civilizations. But these remains are so thoroughly processed by planetary geology that they're invisible to our current detection methods. This perspective also changes how we think about the famous Drake equation, which attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. Most versions of this equation assume that we would be able to detect evidence of alien civilizations if they existed. But if technological signatures fade relatively quickly on astronomical timescales, then the universe might harbor far more past civilizations than we could ever hope to detect. The question of preservation becomes even more complex when we consider the dynamic nature of Earth's surface. Unlike Mars, which preserves features billions of years old in its dry, thin atmosphere, Earth is a geologically active world where the surface is constantly being renewed. Plate tectonics ensure that ocean floors are completely recycled every few hundred million years, carrying any potential evidence down into the mantle where it's destroyed by extreme heat and pressure. Even continental surfaces, which might seem more stable, undergo constant change. Erosion gradually wears down mountains and fills valleys with sediment. Glacial periods advance and retreat, scouring the landscape and depositing new layers of rock and soil. Volcanic activity buries vast areas under layers of lava and ash. In this dynamic environment, the preservation of technological signatures from millions of years ago would require extraordinarily favorable circumstances. Yet despite these challenges, some scientists remain optimistic about the possibility of detecting very ancient civilizations. They point out that certain types of evidence might persist longer than Schmidt and Frank initially calculated. For example, if an ancient civilization had engaged in large-scale mining operations, the resulting changes to mineral distributions might remain detectable for much longer periods. Similarly, if they had created long-lasting radioactive waste or built structures in geologically stable areas, some evidence might survive even millions of years of geological activity. The search for such evidence requires new approaches and technologies. Advanced spectroscopic analysis can detect minute traces of synthetic compounds in ancient rock layers. Sophisticated computer modeling can help distinguish between natural and potentially artificial patterns in geological data. As our analytical capabilities improve, we may discover signatures that have been hiding in plain sight all along. This brings us to one of the most humbling aspects of deep time: the realization that we are not separate from this vast story, but intimately connected to it. Every atom in our bodies has participated in this cosmic recycling for billions of years. The carbon in our cells was once part of ancient atmospheres. The calcium in our bones was formed in the hearts of dying stars. And the water we drink has cycled through countless organisms and geological formations since Earth's early days. As we drift deeper into this contemplation of deep time, we begin to see that the question of whether we're the first civilization on Earth isn't just about technology or intelligence. It's about our place in the vast continuum of existence, our connection to processes that began long before our species emerged and will continue long after we're gone. Whether we're first or latest, pioneers or inheritors, we are participants in something magnificent: the universe's ongoing experiment with complexity, consciousness, and perhaps wisdom itself. The profound implications of deep time perspective extend to how we view our current moment in Earth's history. If we truly grasp the vastness of geological time and the ephemeral nature of technological signatures, we might develop a different relationship with our own civilization's legacy. Knowing that our greatest achievements may leave no detectable trace after just a few million years could inspire us to focus more on sustainable approaches to planetary stewardship rather than monuments to our technological prowess. This temporal perspective also offers a unique form of cosmic comfort. If previous civilizations did exist and face similar challenges to our own, then we're not alone in confronting the difficulties of technological development on a finite planet. Perhaps they found solutions we haven't imagined, developed wisdom we're still learning, or discovered ways to live in harmony with natural systems that sustain them for eons. As we prepare to explore the specific evidence that might support the existence of previous civilizations, we carry with us this fundamental understanding: Earth's history is so vast and the preservation of evidence so challenging that we must approach these questions with both scientific rigor and intellectual humility. The absence of obvious evidence for past civilizations might tell us more about the nature of time and preservation than about the rarity of intelligence in the cosmos. In this first chapter of our journey through deep time, we've established the foundation for everything that follows: an appreciation for the almost incomprehensible scale of Earth's history, and an understanding of why evidence for ancient civilizations might be far more difficult to detect than we initially assumed. As we move forward, we'll examine the tantalizing clues that do exist, explore the cycles of habitability that might have enabled multiple experiments with intelligence, and consider what the implications might be for our own civilization's future. Rest easy in knowing that whether we're first or latest in this cosmic story, we are here now, conscious and curious, adding our own unique voice to the vast conversation between matter and mind that has been unfolding on this remarkable planet for billions of years. The mystery itself is part of the beauty, and in embracing that mystery, we open ourselves to wonder, wisdom, and the profound peace that comes from recognizing our place in the infinite dance of existence. Let's move to our second part of the documentary. We now turn our attention to the ancient world, a place where myth, bones, stone, and the mysterious ingenuity of lost peoples converge. The dead speak through what they left behind, and their whispers weave together the tapestry of our shared human experience, rich with lingering anomalies and riddles that both intrigue and perplex modern minds. As you settle deeper into comfortable rest, we begin with the megalithic monuments that dot the landscapes, silent sentinels from ages lost to history. These structures are more than remnants of ancient labor. They are records, inscribed not with ink, but with stone and astronomical precision. The Great Pyramid of Giza, standing for more than 4,500 years, is perhaps the most iconic. Its blocks, some weighing up to 70 tons, were transported, cut, and fitted with an accuracy that baffles even contemporary engineers. Its base is nearly a perfect square, level within 2 centimeters, and its sides are oriented almost exactly to true north, to a fraction of a degree. Questions abound. What techniques did these builders possess? What knowledge enabled such accomplishment? And might this be the legacy not merely of brilliant human minds, but of technological memory far older than we expect? Move your thoughts to the remote highlands of Peru, where the stones of Sacsayhuaman interlock without mortar so tightly that a piece of paper cannot pass between them. Modern tools would struggle to replicate such craftsmanship, especially given that the stones themselves are irregular in shape and immense in mass. No written record describes how these fortresses were built, or how generations later their secrets faded into legend. The mysteries of megalithic construction are not isolated to isolated cultures. They emerge again and again, from Stonehenge to the Moai of Easter Island to the temples scattered along the Nile and the Indus. Amidst these monuments, we find devices and technologies that seem out of step with their time. The Antikythera mechanism, discovered among the remains of a shipwreck off the coast of Greece in 1901, is sometimes called the world's first analog computer. Crafted over 2,000 years ago, it contains more than 30 bronze gears and was reportedly used to predict astronomical cycles, the orbits of planets, lunar phases, and solar eclipses. When the mechanism was first studied, its sophistication seemed impossible. It would not be until the Enlightenment that similar mechanical precision would be achieved in Europe. And yet here it lay, testimony to a lost tradition of gears, cogs, and cosmic calculation. Nearby, in time and place, we find the so-called Baghdad battery, a clay jar with a copper tube and iron rod that, when filled with vinegar or wine, generates a modest electric current. Was it an accidental discovery, a product of corrosion and the coincidence of available materials, or a genuine technology employed for electroplating or medical treatment? The answer remains uncertain, yet the object stands as another puzzle piece in the great mosaic of human invention, a mosaic that may have origins deeper and older than the accepted timeline of innovation. Traveling further east, we encounter the secrets of ancient metallurgy. Damascus steel, forged in Syria and India between the 3rd and 17th centuries, produced blades of extraordinary strength, able to cleave iron and retain their sharpness through countless battles. The distinctive watered pattern that characterizes Damascus steel was more than ornamental. It pointed to structural intricacies at the nanoscale, including carbon nanotubes, which modern science only began to investigate in the last few decades. For centuries, the secret of this steel was lost, and only recently have researchers begun to reconstruct the processes that once allowed ancient blacksmiths to manipulate atoms unknowingly. If such knowledge can vanish, what other secrets of unprecedented technology might have dissipated in the mists of time long before recorded history? Roman concrete, made over 2,000 years ago, has withstood the elements and the assaults of nature far better than its modern counterpart. Harbors, aqueducts, and temples built by Roman engineers stand strong to this day, their material apparently growing harder with time. It wasn't until the 21st century that geological analysis revealed the reason. Volcanic ash mixed with lime created a self-healing concrete, able to interact with seawater in a way that modern Portland cement cannot. If we had lost the formula for this enduring substance, what else has been forgotten? How many technologies, perhaps essential to the daily lives of vanished peoples, have become irretrievable due to the fragile nature of oral tradition and historical memory? The stories of lost knowledge aren't confined to material artifacts. Take, for instance, the astronomical wisdom encoded in architectural alignments. The pyramids of Egypt, the temples of Angkor Wat, the city plans of Teotihuacan, the stone circles of Northern Europe, all display an uncanny awareness of celestial events. Sites are aligned to solstices, equinoxes, lunar standstills, and notable star risings, far beyond the reach of simple observation. How did ancient cultures reliably calculate these alignments, often requiring generations of recorded observation to achieve? The Mayan calendar, so precise in its reckoning of planetary cycles, still defies complete understanding. Its method of interlocking periods, zero-based counting, and the long count system point to a mathematics sophisticated in ways sometimes lost on modern students. As you drift deeper into sleep's embrace, ponder the question of written language and its preservation. Writing itself is a relatively recent innovation, with the earliest cuneiform and hieroglyphic texts dating back just 6,000 years, a fifth of human existence. Most of what we know about ancient civilizations is constrained by what they chose to record, and how fortunate we are to have found their scripts undisturbed by time and weather. Yet even now, more than half of ancient scripts remain undeciphered. Linear A, used by the Minoans of Crete, resists translation. The Rongorongo tablets of Easter Island remain unread. How many stories, scientific principles, and philosophies lie encoded, inaccessible yet tantalizingly close. If a civilization predating human record existed, what chance would its messages have of surviving the relentless churn of time? Archaeologists sometimes discover objects out of place in the historical record. These so-called out-of-place artifacts range from the Piri Reis map, which shows parts of Antarctica's coastline long before it was discovered, to metal spheres embedded in billion-year-old rock, to the enigmatic Dendera light carvings, interpreted by some as evidence of ancient electrical technology in Egypt. Most mainstream scholars offer more mundane explanations for such finds, but their existence provokes wonder and speculation about alternative histories and the possibility of lost civilizations. Shifting to the arena of bones and fossils, we enter yet another realm of uncertainty and intrigue. The fossil record is riddled with gaps, regions of evolutionary history where transitional forms should exist, yet evidence remains sparse or missing altogether. The sudden appearance of anatomically modern humans approximately 200,000 years ago is a persistent puzzle. The so-called Cambrian explosion, 541 million years ago, saw the rapid diversification and proliferation of complex animal life, including nearly all major animal phyla. Charles Darwin called this a thorny objection to his theory of slow, gradual evolution. How could such diversity emerge in a geologically brief period? Some paleontologists posit that earlier life forms simply failed to fossilize, while others suggest novel genetic or environmental factors enabled diversification. Could there be a deeper explanation? What if the Cambrian explosion represents a reboot of complexity after a long period of evolutionary stasis or even collapse, a resurgence following a mass extinction that nearly sterilized Earth? Such extinction events, including the Great Oxygenation Event and the Snowball Earth glaciations, subjected life to incomprehensible pressures. Evidence from deep-sea vents, where life flourishes without sunlight, suggests that even during global catastrophes, biology finds niches in which to survive and eventually thrive. Microbial communities deep beneath the Earth's crust demonstrate metabolism and growth so slow that reproduction occurs on timescales measured in centuries, not hours or days. These hidden biospheres, disconnected from surface events, may hold secrets about resilience, adaptation, and the persistence of life through the harshest epochs. The idea that cycles of destruction and renewal could also occur in the development of intelligence is both sobering and stimulating. We observe mass extinctions regularly punctuating the history of life. The Permian-Triassic extinction wiped out 96% of marine species and 70% of terrestrial vertebrates. The asteroid impact that marked the end of the Cretaceous era wiped out the dinosaurs, clearing ecological space for mammals and ultimately humanity. What if intelligence, like species, must endure cycles of loss and resurgence? Could earlier civilizations have met their end in natural disasters, climate catastrophes, or even self-inflicted technological collapse? Their memory erased by time, but their influence preserved in subtle ways across generations? Anthropological mysteries further deepen the puzzle. Consider Göbekli Tepe, an ancient site in modern-day Turkey, built roughly 12,000 years ago, prior to the accepted beginning of established agriculture, and adorned with stone pillars intricately carved with animals and symbols. The site's existence challenges the prevailing notion that agriculture made complex society possible. Here, we have evidence of advanced construction and social coordination predating settled farming. Its deliberate burial adds another layer of intrigue. Was it hidden to preserve it, or as part of a ritual of abandonment? Either answer broadens our understanding of the capabilities and priorities of prehistoric cultures. In North America, the Mississippian mound cultures constructed immense earthworks and social centers, such as Cahokia, housing thousands of people. These societies appear to have practiced astronomy, complex ritual, and large-scale urban planning long before European contact. Their disappearance remains enigmatic, a sudden collapse possibly due to overexploitation, climate change, or disease, leaving behind mute earthworks slowly reclaimed by forest and floodplain. In South Asia, the Indus Valley civilization flourished for nearly 1,000 years, with cities that had running water, sewage systems, and organized grids predating similar advances in other regions by centuries. Yet, like many ancient societies, its written records remain untranslated, and its sudden decline, perhaps due to climate change, shifting rivers, or resource depletion, leaves more questions than answers. Turning to the realm of mythology and oral tradition, we find stories of floods, lost lands, and vanished civilizations repeated in cultures around the world. The tale of Atlantis, described by Plato, is often interpreted as an allegory, but elements of its sudden submergence and forgotten glory resonate with flood myths from Mesopotamia, India, Mesoamerica, and beyond. These stories may encode memories of actual disasters, tsunamis, volcanic eruptions, or sea level rises experienced by ancient peoples. Yet some argue for deeper meaning. That myth is a vehicle for transmitting knowledge across generations, even when written language is unknown or forbidden. Such transmission is evident in language itself, with Proto-Indo-European roots linking cultures from India to Iceland, suggesting ancient exchanges of ideas, agriculture, astronomy, philosophy, and more. The Polynesian navigators, using star maps and oral tradition, crossed vast stretches of ocean long before written charts or compasses, evidencing sophisticated understanding of planetary cycles and environmental cues. Imagine now, with every breath, the persistence and spread of ancient wisdom, crossing boundaries of language and geography. How much have we truly inherited? And how much has been lost, waiting to be rediscovered? The field of genetic archaeology opens yet another window into the past, tracking migrations, population bottlenecks, and exchanges across continents. Humanity's genetic code preserves evidence of encounters with Neanderthals, Denisovans, and other hominins. Ancient DNA extracted from bones and teeth reveals patterns of disease, adaptation, and sudden change. Bottlenecks in genetic diversity, such as those occurring at the end of the last ice age, suggest dramatic population contractions and recoveries. Did these bottlenecks result only from climate shifts, or could they reflect the collapse and resurgence of technologically oriented peoples? The study of natural reactors, such as the Oklo phenomenon in Gabon, Africa, presents another form of anomaly. Over 2 billion years ago, specific geological conditions created self-sustaining nuclear reactions, altering the isotopic composition of surrounding rock in ways remarkably similar to human nuclear waste. If natural processes can mimic the technological markers of advanced civilizations, how do we distinguish between ancient industry and geological coincidence? Recent advances in satellite archaeology and remote sensing have dramatically expanded our ability to detect the remnants of lost societies. Massive cities, road networks, and ceremonial sites once hidden beneath jungle canopy or desert sands now reveal themselves through subtle changes in vegetation, elevation, or thermal emission. Machine learning algorithms trained on patterns of known sites now hypothesize, with growing certainty, the potential locations of thousands of still unexplored structures. If technology enables us to see what was invisible, what might lie undiscovered in the depths of ocean, mountain, or forest? Could it yet allow us to discern the faint fingerprints of even earlier builders from epochs lost to the passage of geological time? Scientists have begun to apply similar methods to the search for technosignatures beyond Earth. They examine planetary atmospheres for trace gases, industrial pollutants, synthetic molecules, even the spectral fingerprint of artificial light. If such investigations can reveal life on distant worlds, might they someday allow us to scan the strata of our own planet for unnatural compounds, persistent pollutants, or the metallic residues of vanished machines? Approaching the ancient world with humility, curiosity, and ever-improving tools, we learn more with each passing generation. The interplay between memory, material, and meaning continually reshapes our understanding. We discover that lost technologies can sometimes be reinvented, forgotten wisdom recovered, and that the world's greatest mysteries endure precisely because they invite deeper investigation rather than simple solutions. As listeners, we must also recognize the dangers of sensationalism, misinterpretation, and wishful thinking. Not every irregular artifact, inexplicable structure, or gap in the record points to a vanished civilization or contact with non-human intelligences. Scientific rigor demands careful analysis, critical skepticism, and patient accumulation of evidence. Yet it is equally true that progress often follows wonder, that curiosity drives discovery, and that openness to possibility keeps the search ongoing when certainty would have ended it. The questions that shape this chapter are timeless. What did ancient peoples know, and how did they lose their knowledge? Could the world have hosted cycles of intelligent life, technological innovation, and catastrophic loss so complete that virtually all traces have vanished? Are we the inheritors of deep wisdom, or merely the latest experiment in cosmic complexity? As time inexorably marches forward and human civilization adds its own layers to the record, we remain participants in this great cycle of building, forgetting, and rediscovering. Whether on the surface, deep in the earth, or on the far side of myth, the evidence of what has come before will always be elusive, always tantalizing, and always just out of reach, beckoning those with courage, patience, and imagination to continue the search. Let yourself drift further into sleep, holding these questions gently, allowing your subconscious to connect the dots and weave new possibilities. In the endless night of deep history, every dream is a search for meaning, every story a potential rediscovery, and every moment a chance to participate in the unfolding mystery of human existence. This is how the ancient world invites us, with open questions, unanswered riddles, and the persistent challenge to look closer, think deeper, and listen more carefully to what the bones, stones, symbols, and stories are telling us. If we are not the first, then perhaps the greatest secret lies ahead, waiting for those who dare to dream beyond the limits of recorded history, beyond what is merely known, and into the infinite expanse of what might yet be. Let's move to our third part of the documentary. We now descend into the deepest layers of Earth's memory, where rocks whisper secrets spanning billions of years and fossils tell stories of life's most dramatic transformations. Here, in the geological record, we search for traces of intelligence that might predate humanity by eons, examining the very bones of our planet for evidence of civilizations lost to time itself. As you settle into deeper relaxation, imagine yourself as a time traveler, moving backward through Earth's vast history. Each layer of rock beneath your feet represents millions of years, each fossil a moment frozen in stone. The geological record is our planet's autobiography, written in sediment, volcanic ash, and the compressed remains of ancient life. Yet, like any ancient text, this autobiography has missing pages, entire chapters erased by the relentless forces of erosion, volcanism, and tectonic activity. In these gaps, these silences in stone, might lie the evidence of previous experiments with intelligence. The concept of deep time challenges our most fundamental assumptions about permanence and preservation. Consider that virtually everything we see around us today, mountains, valleys, even the continents themselves, are temporary features on geological timescales. The Himalayan mountains, seemingly eternal and immutable, are actually among Earth's youngest major mountain ranges, having formed only 50 million years ago when the Indian subcontinent collided with Asia. Before that collision, the rocks that now form Everest lay beneath ancient seas, accumulating layers of marine sediment that would later be thrust skyward into the world's highest peaks. This dynamic nature of Earth's surface poses profound challenges for detecting ancient civilizations. Unlike Mars, where features billions of years old remain preserved in the planet's thin, dry atmosphere, Earth constantly renews itself. The oceanic crust, which covers more than 2/3 of our planet's surface, is completely recycled every 200 million years through the process of plate tectonics. Ancient ocean floors are drawn down into the mantle at subduction zones, where they're melted and reformed, carrying with them any evidence they might have contained of past life or technology. Even continental surfaces, which might seem more stable, undergo constant transformation. The Appalachian Mountains, once as tall as today's Himalayas, have been worn down by 300 million years of erosion into the gentle hills we see today. The Colorado River has carved the Grand Canyon in just 6 million years, slicing through rock layers that span nearly 2 billion years of Earth's history. If natural forces can reshape landscapes so dramatically, what chance would artificial structures have of surviving geological time? The fossil record itself reveals the challenges of preservation across deep time. Despite the billions of organisms that have lived and died on Earth, we have fossil evidence for less than 1% of all species that have ever existed. The conditions required for fossilization are extraordinarily specific and rare. An organism must be buried rapidly after death, usually by sediment or volcanic ash, in an environment where oxygen is limited and decomposition is slowed. The surrounding sediment must then remain undisturbed for millions of years while minerals gradually replace the organic material, creating a stone replica of the original form. Even when these conditions are met, the resulting fossil faces additional challenges. Geological processes can destroy fossil-bearing rock layers through heat, pressure, and chemical alteration. Mountain building events can fold and fracture rock layers, breaking apart delicate fossils. Weathering and erosion constantly work to expose and destroy fossil-bearing formations. The result is a fossil record that becomes increasingly sparse as we look further back in time. Not necessarily because life was less abundant, but because older rocks have had more opportunities to be destroyed or altered beyond recognition. This preservation bias, known as the pull of the recent, means that our understanding of ancient life becomes increasingly fragmentary as we peer deeper into the past. The Cambrian explosion, that remarkable period 541 million years ago, when complex animal life suddenly appeared in the fossil record, may not represent the first emergence of complex organisms, but rather the first time that conditions were favorable for their preservation as fossils. Earlier complex life forms may have existed, but left no trace due to their soft bodies or the lack of suitable preservation environments. The implications for detecting ancient technological civilizations are sobering. If we have fossil evidence for less than 1% of biological species, what are the odds of preserving technological artifacts across geological time? Modern materials like steel, aluminum, and concrete, which seem so permanent to us, would decompose relatively quickly once maintenance ceased. Steel rusts away within centuries in most environments. Aluminum, though more durable, would eventually corrode and disperse. Even our most impressive structures would crumble and be scattered by natural forces within thousands of years. However, certain types of evidence might persist longer than others. Large-scale mining operations could leave geological signatures detectable millions of years later. If an ancient civilization had extensively mined rare earth elements or precious metals, the resulting changes to ore distributions might remain visible in the geological record. Similarly, large-scale engineering projects that moved significant amounts of earth and rock could potentially leave traces, though distinguishing these from natural geological processes would be extremely challenging. The search for ancient technological signatures requires us to think beyond traditional archaeology and consider what geochemist Jan Zalasiewicz calls technofossils, the geological traces that technological civilizations might leave behind. Our current civilization is already creating a distinctive geological signature that future researchers might recognize. We've altered the chemistry of the atmosphere, pumping billions of tons of carbon dioxide into the air and changing its isotopic composition in ways that will be detectable in ice cores and marine sediments for thousands of years. Our nuclear weapons testing has scattered artificial radioactive isotopes across the globe, creating a distinct marker horizon that geologists of the future might use to date rock layers. We've created entirely new materials, plastics, synthetic fibers, industrial chemicals, that don't occur in nature and represent clear evidence of technological activity. We've also triggered what many scientists consider the sixth mass extinction, dramatically altering the planet's biodiversity in ways that will be visible in the fossil record for millions of years. Yet even these seemingly permanent markers of our technological civilization would fade over geological time. Atmospheric carbon dioxide is absorbed by natural processes. The oceans, weathering of rocks, and biological activity, and levels return to pre-industrial baselines within hundreds of thousands of years. Radioactive isotopes decay according to their half-lives, with most artificial radioisotopes becoming undetectable within a few million years. Even our persistent plastics, though they might survive longer than most organic materials, would eventually break down under the combined assault of ultraviolet radiation, oxidation, and bacterial decomposition. The realization that technological signatures fade relatively quickly on geological timescales helps explain one of the most puzzling questions in astrobiology, the Fermi paradox. If the universe is so vast and so old, filled with billions of potentially habitable planets, why haven't we detected evidence of extraterrestrial civilizations? One possible answer is that technological civilizations are actually quite common, but their signatures are so ephemeral that we can only detect them during the brief period when they're actively producing detectable signals. This temporal selection effect could mean that the galaxy is littered with the remains of past civilizations, but these remains are so thoroughly processed by planetary geology that they're invisible to our current detection methods. If this is true for alien civilizations, it could also be true for previous terrestrial civilizations. The absence of obvious evidence for past technological activity on Earth might not indicate that such activity never occurred, but rather that we lack the tools and techniques necessary to detect such ancient signatures. Recent advances in analytical chemistry and mass spectrometry are beginning to provide new tools for this search. Scientists can now detect trace amounts of synthetic compounds in environmental samples, identify unusual isotopic ratios that might indicate technological processes, and analyze the chemical composition of ancient rocks and sediments with unprecedented precision. These techniques have already revealed surprising details about Earth's past environments and the evolution of its atmosphere and oceans. The study of impact structures, craters left by asteroid and comet impacts, provides another window into deep time preservation. Some impact craters on Earth are billions of years old, their signatures preserved despite eons of geological activity. If an ancient civilization had been present during a major impact event, traces of their technology might be preserved within the impact structure itself, protected from normal weathering and geological processes by the unique conditions created during such catastrophic events. Ocean sediments represent another potential repository for ancient technological signatures. The deep ocean floors accumulate sediment at extremely slow rates, sometimes just millimeters per thousand years, creating detailed records of past environmental conditions. While most oceanic crust is eventually subducted and destroyed, some ancient sediments are preserved in continental margins and deep ocean basins. These sediments might contain chemical traces of ancient atmospheric compositions, including potential technological pollutants. Ice cores from Antarctica and Greenland preserve detailed records of atmospheric chemistry going back hundreds of thousands of years. While this timescale is far too recent to capture evidence of pre-human civilizations, the techniques used to analyze ice cores could potentially be applied to other materials that preserve longer-term atmospheric records. Certain types of cave formations, for example, grow continuously for millions of years and might preserve chemical signatures of ancient atmospheric compositions. The search for ancient biomarkers, chemical signatures of past life, has revolutionized our understanding of early Earth environments. Scientists can now detect traces of biological activity in rocks over 3.5 billion years old, far older than any preserved fossils. These same techniques might eventually be applied to search for technological markers, chemical signatures that could only be produced by intelligent activity. One of the most intriguing possibilities is the preservation of artificial isotopic ratios. Nuclear processes, whether natural or artificial, create distinctive patterns of isotopic abundance that can persist for millions of years in the right geological environments. The natural nuclear reactors that operated at Oklo in Gabon 2 billion years ago created isotopic signatures that are still detectable today, despite the enormous span of time involved. If an ancient civilization had developed nuclear technology, similar isotopic anomalies might still be detectable in ancient rock formations. Large-scale geoengineering projects might also leave detectable traces. If an ancient civilization had attempted to modify their planet's climate by altering atmospheric composition or ocean chemistry, such changes might be preserved in the geological record. Similarly, extensive use of certain metals or minerals could alter their natural distribution patterns in ways that might remain detectable millions of years later. The concept of the Great Unconformity, a gap in the geological record where rock layers representing hundreds of millions of years are missing, raises intriguing questions about preservation and detection. These gaps, found on every continent, represent periods when existing rock layers were eroded away before new layers were deposited on top. What evidence might have been lost during these periods of intensive erosion? Could traces of ancient civilizations have been erased along with the missing rock layers? Recent discoveries in extreme environments are expanding our understanding of where life can survive and potentially leave traces. Microorganisms have been found living in solid rock kilometers beneath Earth's surface, deriving energy from radioactive decay and chemical reactions with minerals. These deep biosphere communities, completely isolated from surface conditions, have potentially been evolving independently for millions of years. If technological artifacts somehow found their way into these deep environments, they might be preserved far longer than anything on the surface. The emerging field of molecular paleontology is pushing the boundaries of what can be preserved and detected across geological time. Scientists have successfully extracted and analyzed proteins from fossils millions of years old, and some claim to have found preserved organic molecules in rocks over 1 billion years old. While DNA degrades too quickly to survive such timescales, other complex organic molecules might persist much longer, potentially carrying information about their origins. As we contemplate these possibilities, we must also acknowledge the profound challenges involved in distinguishing artificial from natural signatures. Earth is a dynamic chemical system where countless natural processes can create unusual concentrations of elements, distinctive isotopic ratios, and complex organic molecules. Volcanic activity, hydrothermal processes, impact events, and biological evolution all contribute to the planet's chemical complexity. Separating potential technological signatures from this background of natural variation requires not only sophisticated analytical techniques, but also detailed understanding of all the natural processes that might create similar signatures. The statistical nature of this challenge cannot be overstated. Even if ancient technological signatures exist in the geological record, they would likely be extremely rare and might occur in only a tiny fraction of suitable rock formations. Finding such signatures would require analyzing enormous numbers of samples from the right time periods and geological environments, a task that would challenge the resources of the entire scientific community. Yet the potential rewards of such a search extend far beyond the simple question of whether previous civilizations existed on Earth. Understanding how technological signatures are preserved and altered over geological time could inform our search for extraterrestrial intelligence and help us design our own technologies to have maximum longevity. Learning about the environmental impacts of past civilizations might provide insights into managing our own planetary stewardship more effectively. As you drift deeper into contemplation, consider the profound humility that geology imposes on human ambition. The mountains we consider eternal are temporary wrinkles in Earth's surface. The bedrock beneath our feet has been recycled through the planet's interior multiple times. The very continents have wandered across the globe like slow-moving rafts, sometimes joining together into supercontinents, sometimes splitting apart into scattered fragments. In this context of constant change and renewal, the preservation of any evidence across geological time seems almost miraculous. Every fossil represents a vanishingly rare accident of preservation. Every ancient rock formation that survives to the present day has successfully navigated billions of years of potential destruction. If evidence of ancient civilizations exists in the geological record, finding it would require not only advanced technology and enormous resources, but also remarkable luck. This geological perspective transforms our understanding of permanence and legacy. The pyramids, which have stood for less than 5,000 years and already show signs of erosion, represent the blink of an eye in geological terms. Our greatest achievements, from cities to artworks to technological marvels, will eventually return to dust and be recycled into new forms by the patient processes of geology. Yet this impermanence need not inspire despair, but rather a deeper appreciation for the present moment and the miraculous fact that we exist at all in this vast sweep of time. The geological record, with all its gaps and uncertainties, remains our best hope for detecting evidence of previous technological civilizations on Earth. As our analytical techniques become more sophisticated and our understanding of preservation processes deepens, we may eventually develop the capability to detect technological signatures from the deep past. Whether such signatures exist remains an open question, but the search itself will undoubtedly advance our understanding of Earth's history, the nature of technological impact on planetary systems, and our own place in the vast story of life and intelligence in the cosmos. Rest now in the knowledge that you are part of this continuing story, a conscious observer in a universe that has been conducting experiments with matter, energy, and awareness for billions of years. Whether the geological record contains evidence of previous chapters in this story, or whether we are truly the first to read Earth's autobiography with understanding, we remain participants in one of the most remarkable phenomena in the known universe: the emergence of minds capable of contemplating their own origins and wondering about their place in the cosmic story that continues to unfold around us. Let's move to our fourth part of the documentary. We now venture into the vast rhythms of planetary cycles and cosmic time, exploring how Earth itself breathes with changes that span millions of years, creating windows of opportunity for intelligence to emerge, flourish, and perhaps vanish without a trace. Here, in the dance between our planet and the cosmos, we discover that the conditions for complex life are far more delicate and temporary than we might imagine. As you sink deeper into restful contemplation, picture Earth not as a static blue marble suspended in space, but as a living, breathing world that cycles through profound transformations over geological time. Our planet exists in what astronomers call the habitable zone, or Goldilocks zone, that narrow band around the sun where temperatures allow liquid water to exist on a planet's surface. But this zone is not fixed. It changes as our star evolves, and Earth's own position relative to this zone has shifted dramatically throughout its history. The sun, that constant source of warmth and energy that makes life possible, has been gradually increasing in brightness throughout its existence. When Earth formed 4.6 billion years ago, the sun was approximately 30% dimmer than it is today. This presents us with one of astronomy's most intriguing puzzles, known as the faint young sun paradox. With such reduced solar energy, Earth should have been a frozen wasteland for most of its early history. Yet we have clear evidence that liquid water existed on the surface over 4 billion years ago, and life emerged at least 3.8 billion years ago. The resolution to this paradox lies in Earth's early atmosphere, which was vastly different from the thin, oxygen-rich envelope we know today. Our planet's primordial atmosphere was likely much denser and rich in greenhouse gases, carbon dioxide, methane, and water vapor, that trapped heat more efficiently than today's atmosphere. This thick blanket of greenhouse gases compensated for the sun's reduced luminosity, maintaining temperatures that allowed liquid water to exist and life to take hold in ancient seas that bore no resemblance to modern oceans. But this early atmospheric composition was inherently unstable. As life evolved and began to alter the planet's chemistry, dramatic changes followed. The emergence of photosynthesis around 3.5 billion years ago marked the beginning of one of Earth's most profound transformations. Cyanobacteria began converting carbon dioxide and water into organic compounds and oxygen, gradually poisoning the atmosphere with what was, to most early life forms, a deadly gas. The Great Oxidation Event, which occurred around 2.4 billion years ago, fundamentally restructured Earth's atmospheric chemistry. Oxygen levels rose from virtually zero to significant percentages, causing the first mass extinction as anaerobic organisms died off in vast numbers. This event also triggered a severe ice age known as the Huronian glaciation, which may have lasted for 300 million years. The newly oxygenated atmosphere destroyed methane, a powerful greenhouse gas, leading to a dramatic cooling that may have frozen the planet's surface almost entirely. This pattern of atmospheric transformation and climate catastrophe has repeated throughout Earth's history, creating cycles of habitability that rise and fall over millions of years. The planet has experienced at least two, and possibly more, snowball Earth events where ice extended from the poles to the equator, creating a frozen world that seems utterly hostile to complex life. Yet somehow, life not only survived these global ice ages, but emerged from them with renewed diversity and complexity. The most recent snowball Earth episodes occurred between 750 and 580 million years ago, during what geologists call the Cryogenian period. Geological evidence suggests that ice sheets covered virtually the entire planet, with only a few areas of open ocean remaining near the equator. For millions of years, Earth resembled a giant snowball, with surface temperatures plummeting far below freezing and most of the planet's water locked in ice kilometers thick. Yet life found ways to persist even during these extreme conditions. Hydrothermal vents on the ocean floor provided oases of warmth and chemical energy where ecosystems could survive independently of sunlight. Some scientists propose that life may have sheltered beneath the ice, in liquid water layers kept warm by geothermal heating. When the ice ages finally ended, triggered by volcanic carbon dioxide slowly accumulating in the atmosphere, life exploded into new forms of unprecedented complexity. The emergence from the last snowball Earth event coincided with one of the most remarkable episodes in the history of life, the Cambrian explosion. In a geological instant, perhaps 10 to 20 million years, nearly all major animal body plans appeared in the fossil record. This burst of evolutionary innovation occurred around 541 million years ago and established the foundation for all subsequent complex animal life on Earth. The timing of this explosion raises intriguing questions about the relationship between planetary cycles and the emergence of intelligence. Did the extreme conditions of the snowball Earth events somehow accelerate evolution, creating selective pressures that favored more complex and adaptable organisms? Or did the environmental stability that followed these ice ages provide the perfect conditions for evolutionary experimentation and diversification? Throughout Earth's subsequent history, the planet has continued to cycle between greenhouse and icehouse states, each lasting tens of millions of years. During greenhouse periods, such as the Cretaceous period around 100 million years ago, no ice existed anywhere on the planet. Palm trees grew at the North Pole, and sea levels stood 200 meters higher than today. Dinosaurs thrived in these warm, stable conditions, evolving into an astonishing diversity of forms that dominated terrestrial ecosystems for over 160 million years. The transition from greenhouse to icehouse conditions often occurs gradually over millions of years, driven by complex interactions between atmospheric chemistry, ocean circulation, and the arrangement of continents. The formation of supercontinents can disrupt ocean currents and alter global climate patterns. The weathering of rocks, especially during mountain building episodes, can remove carbon dioxide from the atmosphere and trigger cooling. Volcanic activity can either warm or cool the planet, depending on the balance between carbon dioxide emissions and light-blocking particles. These planetary cycles create what we might think of as habitability windows, periods when conditions are particularly favorable for the emergence and flourishing of complex life. The stable, warm conditions of greenhouse periods allow ecosystems to develop complexity and sophistication over millions of years. The challenging but survivable conditions during transitions between climatic states may accelerate evolution and innovation. Even the harsh conditions of icehouse periods and mass extinctions, while devastating to existing life forms, clear ecological space for new evolutionary experiments. The implications for the emergence of intelligence are profound. If technological civilizations require stable environmental conditions to develop, they would be most likely to emerge during the benign phases of these planetary cycles. But if intelligence develops too late in a greenhouse period, it might face the challenges of transitional climate change. If it emerges during an icehouse period, it must contend with unstable conditions and limited resources. The timing of intelligence emergence relative to planetary cycles could determine whether a civilization has millions of years to develop or faces immediate existential challenges. Our own species' emergence illustrates this delicate timing. Homo sapiens evolved during the Quaternary Ice Age, a period characterized by dramatic climate oscillations between glacial and interglacial conditions. The last 2 million years have seen repeated cycles of ice sheet advance and retreat, with glacial periods lasting roughly 100,000 years, interrupted by brief interglacial periods of 10,000 to 20,000 years. We are currently living in one of these interglacial periods, which began about 11,700 years ago. The development of human civilization has occurred entirely within this current interglacial period known as the Holocene. The stable, warm conditions of the Holocene enabled the development of agriculture, which in turn supported larger populations and the emergence of complex societies. But this stability is temporary. Geological evidence suggests that interglacial periods typically end abruptly, sometimes within just a few decades, as the planet tips back into glacial conditions. The precarious nature of our current climatic stability raises questions about the fate of previous experiments with intelligence. If earlier civilizations developed during previous interglacial periods, they would have faced the same challenges we now confront. The knowledge that their benign environmental conditions were temporary and that dramatic climate change was inevitable. How might they have responded to such challenges? Did they develop technologies to weather the transition, or did climate change contribute to their eventual disappearance? The concept of climate-driven civilizational cycles becomes even more intriguing when we consider the role of orbital mechanics in driving climate change. The Serbian mathematician Milutin Milankovic identified 3 astronomical cycles that influence Earth's climate over thousands of years: changes in the shape of Earth's orbit around the Sun, variations in the planet's axial tilt, and the precession of Earth's rotational axis. These Milankovitch cycles create predictable patterns of climate change that repeat over periods ranging from 20,000 to 400,000 years. If ancient civilizations understood these cycles, and there is evidence that some ancient cultures possess sophisticated astronomical knowledge, they might have been able to predict long-term climate trends and plan accordingly. The precision of ancient astronomical alignments at sites like Stonehenge, the pyramids of Giza, and Angkor Wat suggests that some cultures possess detailed knowledge of celestial mechanics. Could this knowledge have extended to understanding the long-term climate implications of orbital cycles? The magnetic field that protects Earth from cosmic radiation also undergoes cyclical changes that could affect the development of life and intelligence. Earth's magnetic field is generated by the motion of molten iron in the planet's core, and this system occasionally undergoes dramatic reversals where magnetic north and south poles switch positions. These reversals occur at irregular intervals, sometimes separated by hundreds of thousands of years, sometimes by just tens of thousands. During magnetic reversals, which can take several thousand years to complete, Earth's magnetic field strength drops dramatically, potentially exposing the surface to increased cosmic radiation and solar particles. While life has clearly survived many such reversals throughout Earth's history, the increased radiation could affect evolution, climate, and the stability of any technological systems that depend on magnetic navigation or are vulnerable to electromagnetic interference. The frequency of magnetic reversals has varied dramatically throughout geological time. During some periods, the magnetic field has remained stable for millions of years. During others, reversals have occurred much more frequently. The current magnetic field has been relatively stable for the past 780,000 years, but recent observations suggest that it may be weakening, possibly indicating that another reversal is approaching. Solar variability adds another layer of complexity to planetary habitability cycles. Our Sun undergoes regular cycles of activity, with sunspot numbers and solar flare activity waxing and waning over approximately 11-year periods. But longer-term solar variations also occur, including grand minima like the Maunder minimum of the 17th and 18th centuries, when solar activity was unusually low, and Earth experienced a period of cooling known as the Little Ice Age. On even longer timescales, the Sun's gradual increase in brightness will eventually make Earth uninhabitable. Current models suggest that in approximately 1 billion years, the sun will be so bright that Earth's oceans will begin to evaporate, triggering a runaway greenhouse effect that will sterilize the planet's surface. This places an ultimate limit on the potential duration of Earth-based civilizations, regardless of their technological capabilities. The interplay between these various cycles, atmospheric evolution, ice ages, magnetic field variations, orbital mechanics, and solar evolution, creates a complex pattern of habitability that changes over multiple timescales. Some periods may be particularly favorable for the emergence and persistence of intelligence, while others may present insurmountable challenges. The history of life on Earth suggests that while life itself is remarkably resilient and adaptable, specific forms of life, including potentially intelligent species, may be much more vulnerable to environmental change. This cyclical view of habitability has profound implications for how we think about the search for previous civilizations. If intelligence tends to emerge during specific phases of planetary cycles, we might expect to find evidence concentrated in particular time periods corresponding to favorable habitability windows. Conversely, the absence of evidence from certain periods might reflect not the absence of intelligence, but the occurrence of those periods during less favorable phases of planetary cycles. The concept also suggests that civilizations might develop differently depending on when they emerge relative to planetary cycles. A civilization that develops during a stable greenhouse period might have millions of years to advance technologically and expand across the globe. Such a civilization might develop capabilities that seem almost magical to us, having had vastly more time than human civilization has enjoyed. Conversely, a civilization that emerges just before a major climate transition might be forced to focus on survival technologies and might never have the stability necessary to achieve high levels of technological sophistication. Recent research into Earth's deep past continues to reveal new complexities in these planetary cycles. The discovery of the Great Unconformity, a gap in the geological record found on every continent, suggests that Earth underwent a period of extensive erosion around 1.2 to 0.8 billion years ago, possibly triggered by severe glaciation or other global catastrophes. This event erased enormous amounts of geological evidence from Earth's Middle Age, potentially including any traces of early experiments with complex life or even intelligence. Similarly, the identification of large igneous provinces, massive volcanic events that have periodically reshaped Earth's surface and atmosphere, reveals that our planet has experienced catastrophic changes that dwarf anything in human experience. The Siberian Traps eruption, which contributed to the Permian-Triassic extinction event 252 million years ago, released such enormous quantities of lava and gases that it fundamentally altered global climate and ocean chemistry. Such events create sharp boundaries in Earth's habitability, potentially ending some evolutionary experiments while setting the stage for others. As you rest in the gentle embrace of sleep, consider the remarkable fact that your existence depends on the precise timing of countless planetary cycles. Had Earth's atmospheric evolution proceeded differently, had the ice ages arrived at different times, had the magnetic field behaved otherwise, the entire trajectory of life on Earth might have been altered. The emergence of human intelligence required not just the right chemical and biological conditions, but the precise alignment of planetary cycles that created a window of opportunity lasting just long enough for consciousness to emerge and begin to understand its own origins. This perspective transforms our understanding of intelligence from an inevitable outcome of evolution to a rare and precious phenomenon that depends on extraordinary alignments of cosmic, planetary, and biological factors. Whether previous intelligences have emerged during earlier favorable periods remains one of the most tantalizing questions in science. But regardless of whether we are first or latest, we exist now in a moment of remarkable planetary grace, conscious participants in cycles that began billions of years before our birth and will continue billions of years after our passing. The rhythms of the planet invite us to think beyond the timescales of human experience and to consider our place in the vast symphony of cosmic cycles that have shaped our world. In this expanded perspective, every moment of consciousness becomes precious, every act of understanding valuable, and every choice to preserve rather than destroy a contribution to the ongoing experiment with intelligence that our planet has been conducting across the eons. Whether we are the first to understand these cycles or the latest in a long line of conscious observers, we are privileged to witness and participate in one of the universe's most remarkable phenomena, the emergence of minds capable of contemplating their own cosmic context and working to ensure that the flame of intelligence continues to burn in the vast darkness of space and time. Let's move to our fifth part of the documentary. We now venture into one of the most haunting questions in all of science, the Great Filter Hypothesis and the profound silence that surrounds us in the cosmos. Here, we explore why the universe, despite its vast age and countless worlds, appears so strangely quiet, and what this cosmic silence might tell us about the fate of civilizations, including potentially our own predecessors on Earth. As you drift deeper into contemplative rest, imagine standing beneath a star-filled sky on a clear night, far from the glow of city lights. Above you stretch hundreds of billions of stars, each potentially hosting planetary systems, many likely harboring worlds not unlike our own. The numbers are staggering. Our Milky Way galaxy alone contains an estimated 400 billion stars, and astronomers now believe that most of these stars have planets orbiting around them. In the observable universe, there may be as many as 2 trillion galaxies, each filled with their own stellar multitudes. The mathematical implications are overwhelming. There should be countless worlds where life has had the opportunity to emerge, evolve, and potentially develop intelligence and technology. Yet when we scan the heavens with our most sensitive instruments, listen with our most sophisticated radio telescopes, and search with our most advanced detection methods, we encounter only silence. This is the essence of the Fermi paradox, named after physicist Enrico Fermi, who first articulated this puzzle during a casual conversation at Los Alamos in 1950. If the universe should be teeming with intelligence, Fermi asked, where is everybody? The question has haunted scientists for decades, spawning countless theories and inspiring one of the most active areas of research in astrobiology. The mathematical foundation of the Fermi paradox rests on the Drake equation, formulated by astronomer Frank Drake in 1961 as a framework for estimating the number of communicating extraterrestrial civilizations in our galaxy. The equation multiplies together factors such as the rate of star formation, the fraction of stars with planets, the number of planets that could potentially support life, the fraction where life actually develops, the fraction where intelligent life emerges, the fraction that develops detectable technology, and the length of time such civilizations remain detectable. Even conservative estimates for these factors suggest that our galaxy should host thousands or even millions of technological civilizations. Yet our searches have revealed nothing. The search for extraterrestrial intelligence, which has been conducting systematic surveys of the sky for over 60 years, has detected no confirmed signals of artificial origin. NASA's Kepler mission and other planet hunting programs have identified thousands of potentially habitable worlds, but none show obvious signs of technological activity. The more we learn about the prevalence of planetary systems and potentially habitable environments, the more puzzling the cosmic silence becomes. This paradox has profound implications for our understanding of intelligence and civilization in the universe. One of the most compelling explanations is the Great Filter Hypothesis, proposed by economist Robin Hanson in 1996. According to this theory, there exists some evolutionary step or challenge that is so difficult, so improbable, or so dangerous that it prevents most potential civilizations from ever becoming detectable across interstellar distances. This filter acts as a cosmic bottleneck, explaining why intelligence appears to be so rare despite the apparently favorable conditions for its emergence. The crucial question, and one that has existential implications for humanity, is where this great filter lies. If the filter is behind us, in the emergence of life itself, the development of complex cells, or the evolution of intelligence, then we may be extraordinarily fortunate to have passed through already. This would make us among the first successful experiments with consciousness in our cosmic neighborhood, pioneers in the universe's long journey toward greater complexity and awareness. While this scenario would make us cosmically special, it would also place upon us the awesome responsibility of being among the first to test whether intelligence can successfully navigate the challenges of technological development. However, if the great filter lies ahead of us, the implications are far more sobering. Perhaps every civilization, no matter how advanced or wise, eventually encounters challenges that prove insurmountable. These might include environmental catastrophes triggered by industrial development, resource depletion that cannot be overcome through technology, warfare enabled by increasingly powerful weapons, or perhaps artificial intelligence that exceeds its creator's ability to control. In this scenario, the cosmic silence doesn't reflect the rarity of intelligence, but rather its tendency towards self-destruction or fundamental limitation. The archaeological record of human civilizations provides sobering examples of how advanced societies can collapse despite apparent success. The Maya civilization, which achieved remarkable sophistication in mathematics, astronomy, and engineering, experienced a mysterious collapse around 900 CE that led to the abandonment of major cities and a dramatic population decline. Theories for this collapse include environmental degradation, warfare, social upheaval, and climate change, but the exact causes remain debated. What's clear is that even highly advanced civilizations can face sudden and catastrophic decline. The civilization of Easter Island provides another cautionary example. Archaeological evidence suggests that the island once supported a sophisticated society capable of creating and transporting the massive Moai statues that still dot the landscape. However, the population appears to have exceeded the island's carrying capacity, leading to deforestation, soil depletion, and eventual societal collapse. When European explorers arrived in the 18th century, they found a fraction of the population that the island had once supported, living in relatively simple conditions among the ruins of their ancestors' achievements. These examples of civilizational collapse take on new significance when viewed through the lens of the Great Filter Hypothesis. If human societies, with all their adaptability and intelligence, regularly face collapse when they outgrow their resource base or destabilize their environment, what does this suggest about the long-term prospects for technological civilizations in general? Could it be that the filter lies not in the emergence of intelligence, but in its ability to develop sustainable relationships with planetary resources and environmental systems? The concept of self-imposed extinction becomes particularly relevant when we consider the destructive capabilities that advanced technology inevitably produces. Nuclear weapons, developed less than a century after the Industrial Revolution began, gave humanity the ability to destroy its own civilization for the first time in its history. The Cuban Missile Crisis of 1962 brought the world terrifyingly close to nuclear war, and only the restraint of a few key individuals prevented what could have been a civilization-ending catastrophe. The fact that we came so close to nuclear annihilation so soon after developing these weapons suggests that the window between achieving destructive capabilities and learning to manage them safely may be vanishingly small. Biological weapons present another existential risk that grows more serious as our understanding of genetics and microbiology advances. The same technologies that promise to cure diseases and enhance human capabilities could also be used to create pathogens far more deadly than anything found in nature. Unlike nuclear weapons, which require rare materials and sophisticated infrastructure, biological weapons could potentially be developed by smaller groups or even individuals with access to advanced laboratory equipment. Artificial intelligence represents perhaps the most complex and uncertain existential risk facing advanced civilizations. While AI promises tremendous benefits, solving complex problems, managing resources efficiently, and perhaps even extending consciousness beyond biological limitations, it also poses unprecedented challenges. The development of artificial general intelligence that equals or exceeds human cognitive abilities could represent either the greatest triumph in the history of consciousness or its ultimate replacement. The critical question is whether biological intelligence can maintain control and alignment with artificial systems that may quickly become far more capable than their creators. Climate change and environmental degradation present another potential filter that every industrial civilization must navigate. The same technologies that enable advanced civilizations, fossil fuel combustion, industrial chemistry, large-scale agriculture, inevitably alter planetary environments in ways that can threaten the stability of the ecosystems upon which civilization depends. Earth's current climate crisis demonstrates how quickly industrial activity can alter global systems, and the difficulty of coordinating effective responses, even when the risks are clearly understood. The challenge becomes even more complex when we consider that technological civilizations may face multiple potential filters simultaneously. A civilization dealing with resource depletion might be more vulnerable to environmental instability, which in turn could increase the likelihood of conflict and reduce the resources available for developing sustainable solutions. The interplay between these various challenges could create cascade effects where problems compound each other in ways that overwhelm even advanced civilizations' ability to respond. Recent research into existential risks has identified additional potential filters that could affect advanced civilizations. Gamma-ray bursts from nearby stars could sterilize planetary surfaces with deadly radiation. Supervolcanic eruptions could trigger climate catastrophes lasting decades or centuries. Asteroid or comet impacts could devastate global ecosystems. While these natural disasters might not permanently end a sufficiently advanced and distributed civilization, they could set back technological development by centuries or millennia, potentially preventing civilizations from achieving the capabilities needed to expand beyond their home planets. The concept of the sustainability bottleneck suggests that civilizations face their greatest existential risk during the transition from growth-based to sustainable economic and technological systems. During this transition, civilizations must fundamentally restructure their relationship with planetary resources while maintaining the social stability and technological capabilities needed to complete the transition. This period might last thousands of years and could prove too challenging for most civilizations to navigate successfully. If the Great Filter Hypothesis is correct and lies ahead of humanity, this could explain not only the cosmic silence, but also the absence of evidence for previous civilizations on Earth. Perhaps our planet has hosted multiple experiments with intelligence, each eventually succumbing to one or more of the challenges that constitute the Great Filter. The geological record's inability to preserve technological signatures over millions of years means that evidence of their existence might have been completely erased, leaving us unaware of our predecessors' struggles and failures. The possibility that previous terrestrial civilizations faced similar challenges to our own raises profound questions about learning and memory across cosmic time. If earlier intelligences developed nuclear technology, experienced climate change, or struggled with artificial intelligence, their solutions or failures are lost to us. Each experiment with intelligence on Earth might have had to rediscover the same fundamental challenges and develop responses without benefit of previous experience. This perspective transforms the concept of civilization from a linear progression toward greater sophistication to a cyclical phenomenon where intelligence repeatedly emerges, faces fundamental challenges, and either transcends them or succumbs to them. The fossil record shows that life itself follows similar patterns, with periods of evolutionary radiation followed by mass extinctions that reset the evolutionary experiment. Perhaps intelligence follows analogous patterns, with periods of technological advancement followed by collapses that clear the stage for new experiments with consciousness. The implications extend beyond individual civilizations to the evolution of intelligence in the cosmos as a whole. If the Great Filter represents challenges that most civilizations cannot overcome, then the universe might be filled with the remains of failed experiments in consciousness. This would make our current moment in human history extraordinarily significant. We might be approaching the same critical tests that have determined the fate of countless other intelligences throughout cosmic history. However, the Great Filter Hypothesis also suggests more optimistic possibilities. If civilizations can successfully navigate the filter, they might achieve capabilities that make them effectively immortal and undetectable to younger civilizations like ourselves. Perhaps advanced civilizations learn to live so efficiently and sustainably that they leave no detectable signatures across interstellar space. Or perhaps they transcend physical existence entirely, existing in forms of consciousness that operate beyond our current ability to detect or comprehend. The concept of the dark forest solution to the Fermi paradox suggests another possibility: that advanced civilizations actively hide from detection because the universe is dangerous for visible intelligences. Perhaps the cosmos is filled with predatory civilizations that eliminate competitors, making invisibility a survival strategy. In this scenario, the apparent silence of the universe would reflect not the absence of intelligence, but its learned caution. If previous civilizations on Earth discovered this cosmic reality, they might have chosen concealment over expansion, leaving no obvious traces of their existence. The search for extraterrestrial intelligence has begun to expand beyond traditional radio signals to look for other potential signatures of advanced civilizations. Astronomers now search for technosignatures, evidence of technology that might be detectable across interstellar distances. These could include industrial pollutants in planetary atmospheres, the waste heat from massive energy systems, artificial structures that block starlight, or even evidence of large-scale engineering projects like Dyson spheres that could harness the entire energy output of stars. The development of increasingly sophisticated detection methods raises the possibility that we might eventually be able to apply similar techniques to our own planet's past. If we can learn to detect the subtle atmospheric and geological signatures of technological civilizations on distant worlds, we might eventually develop the capability to search for similar signatures in Earth's ancient rocks and sediments. This could finally provide definitive answers to the question of whether previous civilizations have existed on our own world. The psychological and philosophical implications of the Great Filter Hypothesis are profound. If we are indeed approaching a cosmic test that has eliminated most previous experiments with intelligence, then our choices in the coming decades and centuries may determine not only our own fate, but our planet's entire legacy of consciousness. Every decision about nuclear weapons, environmental protection, artificial intelligence development, and global cooperation takes on cosmic significance when viewed from this perspective. Yet the Great Filter Hypothesis also offers a form of cosmic purpose and meaning. If we can successfully navigate the challenges that have defeated previous civilizations, we might become part of a select group of intelligences that have transcended the limitations that bind most conscious beings to short-lived local existence. Our struggles with sustainability, our efforts to control destructive technologies, and our attempts to create beneficial artificial intelligence might represent not just practical challenges, but tests of our worthiness to join a cosmic community of successfully filtered civilizations. The silence of the universe, whether it reflects the rarity of intelligence or the difficulty of the challenges it faces, transforms our understanding of human significance in the cosmos. We are not merely one species among billions on one planet among trillions, but potentially one of the few experiments with consciousness that has reached the point of recognizing its own cosmic context and grappling consciously with the challenges that determine civilizational survival. As you drift toward deeper rest, consider that your existence occurs at what may be one of the most critical moments in the history of intelligence on Earth, and possibly in our local region of the universe. The choices made by your generation and those immediately following may determine whether consciousness on Earth joins the cosmic silence or finds ways to transcend the filters that have challenged every intelligence that has ever gazed up at the stars and wondered about its place in the vast, seemingly empty cosmos. The Great Filter reminds us that intelligence, for all its remarkable capabilities, exists within constraints that may be fundamental to the nature of consciousness in a physical universe. Whether these constraints can be transcended, whether the apparent silence of the cosmos conceals a community of successfully filtered civilizations, or whether intelligence inevitably faces insurmountable challenges remains one of the deepest mysteries confronting human understanding. In grappling with these questions, we honor not only our own potential, but perhaps the memory of previous experiments with consciousness that may have walked this path before us, leaving only silence as testimony to their existence and their struggles, with the same fundamental questions that now challenge our own emerging cosmic awareness. Let's move to our sixth part of the documentary, or chapter. Like podcast style, we now turn our attention to the remarkable tools and methods that modern science employs to search for evidence of ancient intelligence, both on our own world and beyond. Here, we explore how cutting-edge technology is revolutionizing our ability to detect the faintest traces of past civilizations, and how these same methods might eventually reveal whether we truly are Earth's first experiment with consciousness. As you settle into deeper tranquility, imagine the sensitive instruments that now scan our planet from space, peer into the deepest ocean trenches, and analyze microscopic traces of ancient chemistry with unprecedented precision. These technological marvels represent humanity's most sophisticated attempt to read the hidden messages written in stone, sediment, and the very atoms that compose our world. Each advance in our detection capabilities opens new possibilities for discovering evidence that previous civilizations may have left behind, traces so subtle that they have remained invisible until now. The search for extraterrestrial intelligence has evolved far beyond the radio telescopes that first listened for alien signals in the 1960s. Today's SETI programs employ arrays of interconnected dishes that can simultaneously monitor millions of star systems across multiple frequency bands. The Breakthrough Listen project, launched in 2015 with $100 million in funding, represents the most comprehensive search for technological signatures ever undertaken, using some of the world's most powerful radio telescopes, including the 100-meter Green Bank telescope in West Virginia and the 64-meter Parkes telescope in Australia. The project can detect signals as weak as those that would be produced by an airport radar at the distance of the nearest star. But perhaps more importantly, for our investigation into Earth's past, these same techniques for detecting artificial signals are being refined to search for technosignatures in our planet's geological record. Just as SETI researchers have learned to distinguish between natural cosmic phenomena and potentially artificial signals, scientists are developing methods to identify chemical and isotopic signatures that could only be produced by technological activity. The principles are similar. Look for patterns, concentrations, or ratios that deviate from what natural processes would produce. Then investigate whether these anomalies could indicate the presence of intelligence. Atmospheric analysis has become one of the most promising avenues for detecting distant civilizations. The James Webb Space Telescope and other advanced instruments can now analyze the chemical composition of exoplanet atmospheres by studying how starlight filters through them during planetary transits. Scientists look for biosignatures, gases like oxygen, methane, or phosphine that might indicate biological activity. But they also search for potential technosignatures such as industrial pollutants, synthetic compounds, or unusual concentrations of gases that might result from large-scale technological processes. The same spectroscopic techniques used to analyze distant atmospheres are being applied to samples from Earth's past. Ice cores, which preserve detailed records of atmospheric composition going back hundreds of thousands of years, are being analyzed with increasing precision to detect trace amounts of synthetic compounds or unusual isotopic ratios. While current ice cores only extend back to the most recent ice age, scientists are exploring whether similar atmospheric records might be preserved in other materials, such as ancient tree resins, cave formations, or even tiny bubbles trapped in ancient rocks. Ocean sediment cores represent another frontier in the search for ancient technosignatures. The deep ocean floors accumulate sediment extremely slowly, sometimes just millimeters per thousand years, creating detailed chronological records of past environmental conditions. Advanced mass spectrometry can now detect parts per billion concentrations of various elements and compounds in these sediment layers, potentially revealing the chemical footprints of ancient industrial activity. Scientists are particularly interested in layers that correspond to major climate transitions or extinction events, periods when environmental pressures might have driven technological development, or when civilizational collapse might have left distinctive chemical signatures. Ground-penetrating radar and other subsurface imaging technologies, originally developed for archaeology and geology, are being refined to detect increasingly subtle anomalies beneath the Earth's surface. These methods can now identify buried structures, altered soil chemistry, or unusual material distributions at depths of several meters. While current limitations prevent detecting artifacts millions of years old, advancing technology may eventually enable the detection of more durable signatures, such as altered mineral distributions resulting from ancient mining operations, or the remains of structures built from materials that resist normal geological processes. Satellite archaeology has revolutionized our understanding of human history by revealing hidden cities, road networks, and agricultural systems invisible from ground level. Advanced imaging satellites can detect subtle variations in vegetation, soil moisture, and surface temperature that indicate human modification of landscapes. Machine learning algorithms trained on patterns from known archaeological sites can now automatically identify potential new sites across vast areas. These same techniques could potentially be applied to search for evidence of much older civilizations, looking for landscape modifications or infrastructure that might have survived geological processes over much longer timescales. The development of quantum sensors promises to bring unprecedented sensitivity to the search for ancient technological signatures. These devices, which exploit quantum mechanical effects to achieve measurements at the fundamental limits of physical precision, can detect gravitational anomalies so small that they might reveal buried structures or unusual mass distributions resulting from ancient engineering projects. Quantum magnetometers can map magnetic field variations with extraordinary precision, potentially identifying areas where ancient metallurgy or electromagnetic technology might have altered local magnetic properties in ways that persist over geological time. Genetic archaeology, while primarily focused on tracing the evolution and migration of species, is also providing new insights into potential technological signatures. Ancient DNA, extracted from fossils, sediment cores, and even cave deposits, can reveal information about past ecosystems, population dynamics, and environmental changes. As techniques for recovering and analyzing ancient genetic material continue to improve, scientists may eventually be able to detect evidence of artificial selection, genetic modification, or other biological technologies that previous civilizations might have employed. The field of molecular paleontology pushes the boundaries of what can be preserved and detected across geological time. Scientists have successfully extracted and analyzed proteins from fossils millions of years old, and some controversial claims suggest that even older organic molecules might survive under exceptional circumstances. While DNA degrades too quickly to survive millions of years, other complex organic molecules, including some synthetic compounds, might persist much longer in the right environments. Advanced analytical chemistry can now identify and characterize these molecules with extraordinary precision, potentially revealing signatures of ancient biochemical or pharmaceutical technology. Isotopic analysis has become one of the most powerful tools for detecting artificial processes in the geological record. Nuclear processes, whether natural or artificial, create distinctive patterns of isotopic abundance that can persist for millions of years. The natural nuclear reactors that operated at Oklo in Gabon 2 billion years ago created isotopic signatures that are still detectable today, providing a template for what artificial nuclear processes might look like in ancient rocks. Scientists are systematically analyzing rocks of various ages and compositions, looking for isotopic anomalies that might indicate prehistoric nuclear technology. The study of rare earth elements and other unusual metal concentrations provides another avenue for detecting ancient technological activity. Modern technology depends heavily on rare earth elements, precious metals, and other materials that don't occur in high concentrations naturally. Large-scale extraction and processing of these materials would create distinctive geological signatures that might persist long after the civilizations that created them disappeared. Advanced X-ray fluorescence and other analytical techniques can now map the distribution of these elements in ancient rocks with unprecedented precision and sensitivity. Deep drilling projects, originally undertaken for geological research or resource exploration, are providing access to rock samples from unprecedented depths and ages. Some drilling projects have reached depths of over 12 kilometers, accessing rocks that are hundreds of millions of years old. These deep samples are being analyzed not only for their geological and biological significance, but also for any potential technological signatures they might contain. The development of better preservation techniques and analytical methods for these deep samples continues to expand the temporal range of our search for ancient civilizations. Artificial intelligence and machine learning are revolutionizing the analysis of geological and archaeological data. AI systems can now process vast data sets from multiple sources: satellite imagery, ground surveys, chemical analyses, and geological records, to identify patterns that human researchers might miss. These systems are being trained to recognize the subtle signatures that technological activity might leave in various types of geological records. As these AI systems become more sophisticated, they may be able to detect evidence of ancient civilizations in datasets that have already been collected but not yet fully analyzed. The integration of multiple detection methods is creating new possibilities for comprehensive searches. By combining satellite imagery with ground-penetrating radar, chemical analysis with isotopic studies, and geological surveys with biological investigations, scientists can build detailed pictures of past environmental conditions and detect anomalies that might not be apparent from any single type of evidence. This multidisciplinary approach is essential because evidence of ancient civilizations, if it exists, is likely to be fragmentary and subtle, requiring multiple lines of evidence to establish convincing cases. The development of automated analysis systems is making it possible to search for evidence of ancient civilizations on scales that were previously impossible. Robotic laboratories can now process thousands of samples per day, analyzing them for dozens of different chemical signatures simultaneously. Automated data analysis systems can identify patterns and anomalies in these vast data sets much more quickly and thoroughly than human researchers. This automation is essential because searching for evidence of ancient civilizations requires analyzing enormous numbers of samples from the right time periods and geographical locations. One of the most intriguing developments is the application of forensic science techniques to geological samples. Methods originally developed for analyzing trace evidence in criminal investigations are being adapted to search for microscopic technological artifacts in ancient sediments. These techniques can detect and analyze individual particles that might be synthetic in origin, even when they occur in concentrations of just a few parts per trillion. Such sensitivity opens the possibility of detecting evidence of ancient technology, even when it has been dispersed and diluted by millions of years of geological processes. The search for ancient civilizations is also benefiting from advances in experimental archaeology. Researchers are conducting controlled studies to understand how different types of technological artifacts and signatures would degrade over various timescales under different environmental conditions. By burying modern materials in different geological settings and monitoring their preservation over years and decades, scientists are developing better models for what might remain detectable after much longer periods. These studies help calibrate search methods and provide realistic expectations for what types of evidence might survive geological time. Climate reconstruction techniques, originally developed to understand natural climate variations, are being refined to detect potential artificial climate modifications. If ancient civilizations developed climate engineering technologies or produced industrial emissions on scales large enough to affect global climate, these changes might be detectable in paleoclimate records. Scientists are developing increasingly sophisticated methods for distinguishing between natural climate variations and changes that might result from technological activity, even when both are preserved in the same geological records. The miniaturization of analytical equipment is making it possible to conduct sophisticated searches for ancient technological signatures in field settings. Portable mass spectrometers, X-ray analyzers, and other instruments can now provide laboratory-quality analyses of geological samples in remote locations. This capability is essential for comprehensive searches because potentially significant samples might be found in locations far from traditional laboratories. The ability to conduct immediate, high-quality analyses in the field allows researchers to make real-time decisions about which samples deserve more detailed study. As you drift deeper into restful contemplation, consider how these advancing search capabilities are transforming our relationship with deep time. Each new analytical technique opens windows into previously inaccessible periods of Earth's history. Every improvement in sensitivity brings us closer to being able to detect the faintest traces of past intelligence, if such traces exist. The technological revolution in search methods means that evidence for ancient civilizations, if it exists, may not remain hidden much longer. The implications extend far beyond the specific question of whether previous civilizations existed on Earth. The same methods being developed to search our planet's past are also being applied to the search for current and past civilizations on other worlds. The techniques for detecting technosignatures in Earth's geological record are closely related to those used to search for evidence of technology in the atmospheres and surfaces of distant planets. As our methods become more sophisticated, we may simultaneously solve both mysteries, whether we are alone in space and whether we are first in time. The convergence of multiple advanced technologies, quantum sensors, artificial intelligence, automated analysis, space-based observation, and molecular-level detection is creating unprecedented opportunities for discovery. For the first time in history, we possess tools sensitive enough to detect the subtle traces that ancient technological civilizations might have left behind. Whether these tools will reveal evidence of previous experiments with intelligence on Earth remains to be seen, but the search itself is advancing our understanding of planetary history, technological impact, and the nature of evidence preservation across geological time. These search methods also provide a sobering perspective on our own civilization's longevity. By understanding how quickly most traces of technology disappear and what types of signatures persist longest, we gain insights into what aspects of our own civilization might remain detectable to future investigators. This knowledge could guide our choices about what legacies to leave and how to design technologies and systems that might survive beyond the immediate future. In searching for evidence of those who came before, we also prepare messages for those who might come after, continuing the eternal conversation between consciousness and cosmos that may span far more of Earth's history than we have yet realized. Let's move to our seventh part of the documentary. We now venture into the vast cosmic perspective that places our entire inquiry within the greater tapestry of universal evolution, consciousness, and meaning. Here, we explore what it means to be aware beings in a cosmos that may have witnessed countless experiments with intelligence across billions of years, the infinite dance of existence, and how this possibility transforms our understanding of our place in the infinite dance of existence. As you settle into the deepest layers of contemplation, imagine yourself suspended in the cosmic web, that magnificent structure of dark matter and galaxies that spans the observable universe. From this vantage point, billions of light years from Earth, our entire solar system would be invisible, lost among the hundreds of billions of stars that populate the Milky Way galaxy. Yet from this cosmic perspective, the questions we've been exploring take on even greater significance. If Earth has hosted multiple experiments with intelligence across its 4.6 billion year history, then consciousness itself may be a far more fundamental and persistent feature of the cosmos than we have ever imagined. The philosophical implications of this possibility extend to the very nature of consciousness and its role in the universe's evolution. Carl Sagan once observed that we are the universe becoming aware of itself. Through human consciousness, matter has achieved the remarkable feat of contemplating its own existence, origins, and destiny. But if consciousness has emerged repeatedly throughout Earth's history, then this achievement may not be unique to our current moment. Perhaps the universe has been becoming aware of itself through countless minds across geological time, each contributing its own perspective to the cosmic conversation between matter and awareness. This expanded view of consciousness challenges our most fundamental assumptions about the relationship between mind and cosmos. Traditional Western philosophy has often treated consciousness as an emergent property that arose late in the universe's evolution, a kind of cosmic afterthought that appeared only when matter achieved sufficient complexity. But if intelligence has emerged multiple times throughout Earth's history, consciousness begins to look less like an accident and more like an inevitable outcome of universal evolution, as fundamental to the cosmos as stars, galaxies, and the complex chemistry that enables life itself. The concept of cosmic evolution provides a framework for understanding how consciousness might fit into the larger story of universal development. Just as the universe has evolved from simple hydrogen and helium to complex atoms, molecules, and eventually living systems, perhaps consciousness represents the next stage in this progression toward greater complexity and organization. From this perspective, intelligence is not separate from cosmic evolution, but integral to it, the means by which the universe develops. The capacity for self-reflection, understanding, and perhaps even self-direction. If previous civilizations on Earth achieved high levels of technological and intellectual sophistication, they may have grappled with the same fundamental questions that now occupy human philosophers and scientists. What is the nature of consciousness? How does mind relate to matter? What is our responsibility as aware beings in a cosmos that has given rise to awareness? The possibility that these questions have been contemplated by other intelligences across geological time adds poignancy and depth to our current inquiries, suggesting that we may be participating in an ancient dialogue that spans far more of Earth's history than we realize. The search for previous civilizations also raises profound questions about the nature of knowledge and wisdom across cosmic time. Human civilization has made remarkable progress in understanding the physical universe, developing mathematics, science, and technology that would seem miraculous to our ancestors of just a few centuries ago. But if earlier civilizations had millions of years to develop their understanding, rather than the mere 10,000 years that have elapsed since the agricultural revolution, what insights might they have achieved? Could they have solved problems that still challenge us, developed technologies we cannot imagine, or achieved forms of wisdom that transcend anything in our current experience? The possibility of cyclical intelligence on Earth also transforms our understanding of progress and development. Human civilization has generally assumed that knowledge and capability advance linearly over time, with each generation building upon the achievements of previous ones. But if civilizations rise and fall in geological cycles, separated by millions of years of forgetting, then progress becomes cyclical rather than linear. Each experiment with intelligence might have to rediscover fundamental truths about nature, consciousness, and cosmic purpose, developing their own unique perspectives on timeless questions. This cyclical view of intelligence has precedence in many philosophical and religious traditions. Hinduism describes vast cosmic cycles where universes are born, evolve, and dissolve, only to be reborn in endless repetition. Buddhism speaks of countless aeons during which consciousness evolves toward enlightenment, with each being contributing to the overall awakening of cosmic awareness. Indigenous wisdom traditions often describe cycles of worlds, each with its own forms of life and consciousness, each contributing to the ongoing evolution of spiritual understanding. Perhaps these traditional cosmologies, often dismissed by modern science as primitive mythologies, actually preserve deeper truths about the cyclical nature of consciousness and intelligence. If previous civilizations achieved profound insights into the nature of reality and cosmic purpose, some of these insights might have been preserved in symbolic form in myths, legends, and spiritual traditions that have survived across millennia. The recurring themes in human mythology, Stories of lost golden ages, fallen civilizations, and cycles of creation and destruction might contain encoded memories of actual historical events that occurred on timescales far longer than recorded history. The cosmic perspective also illuminates the profound interconnectedness of all forms of consciousness, whether human, potentially pre-human, or perhaps even non-terrestrial. Every atom in our bodies was forged in the nuclear furnaces of stars that lived and died long before Earth formed. The carbon in our cells, the calcium in our bones, the iron in our blood, all were scattered into space by stellar explosions and eventually incorporated into the planetary disk from which Earth condensed. We are literally made of star stuff, cosmic matter organized into forms capable of contemplating their own cosmic origins. If previous civilizations existed on Earth, they too were composed of this same stellar material, rearranged by evolutionary processes into different patterns of consciousness and awareness. The atoms that once formed their bodies have been recycled countless times through geological processes, perhaps now forming part of our own bodies or those of other living beings. In this deep material sense, we are connected not only to all current life on Earth, but potentially to all consciousness that has ever existed on our planet. This material continuity extends to the information dimension as well. While the specific knowledge and cultural achievements of previous civilizations might be lost, their influence on the evolutionary trajectory of life and consciousness might persist in subtle ways. If earlier intelligences modified their environment, influenced the evolution of other species, or left chemical or biological traces in the planetary system, their legacy might still be affecting the development of consciousness today. We might be the inheritors of influences we cannot recognize, shaped by the activities of minds that contemplated the cosmos millions of years before human intelligence emerged. The question of whether we are alone in time connects directly to the larger question of whether we are alone in space. The same cosmic processes that might have given rise to multiple experiments with intelligence on Earth, stellar nucleosynthesis, planetary formation, chemical evolution, biological development, are operating throughout the universe. If consciousness can emerge repeatedly on a single world given sufficient time, then the cosmos as a whole might be teeming with forms of awareness we have not yet learned to recognize or detect. This possibility transforms our understanding of the search for extraterrestrial intelligence. Rather than looking for civilizations similar to our own current stage of development, we might need to search for forms of consciousness that have had millions or billions of years to evolve beyond anything we can currently imagine. Such advanced forms of awareness might exist in states so different from human consciousness that we lack the conceptual frameworks necessary to recognize their presence or understand their activities. The cosmic perspective also suggests that consciousness itself might evolve according to principles we are only beginning to understand. Just as biological evolution has produced an enormous diversity of life forms adapted to different environments and ecological niches, the evolution of consciousness might produce diverse forms of awareness adapted to different cosmic contexts. Some forms of consciousness might be optimized for rapid technological development, others for deep contemplation and understanding, still others for integration with natural systems, or for expansion across cosmic distances. If previous terrestrial civilizations explored these different modes of consciousness development, they might have achieved forms of awareness that transcend the boundaries of individual minds or even individual species. Perhaps they learned to create collective forms of consciousness that spanned entire ecosystems, or developed technologies that allowed individual minds to merge into larger patterns of awareness. Such achievements would be nearly impossible to detect using conventional archaeological methods, but their effects might still influence the development of consciousness in ways we are only beginning to recognize. The relationship between consciousness and the physical universe remains one of the deepest mysteries in science and philosophy. How does the subjective experience of awareness arise from objective physical processes? What is the relationship between the mental and material dimensions of reality? These questions take on new dimensions when considered from the cosmic perspective of potentially cyclical intelligence. If consciousness has emerged multiple times throughout Earth's history, each instance might have contributed unique insights into the fundamental nature of mind and its relationship to the cosmos. Some advanced civilizations might have achieved integration between consciousness and physical reality that transcends our current understanding of both. They might have discovered that the distinction between mind and matter is less fundamental than it appears, or developed technologies that work by directly interfacing with the quantum foundations of physical reality. Such achievements would represent not just technological advancement, but fundamental breakthroughs in our understanding of the nature of existence itself. The cosmic perspective also raises questions about the ultimate purpose and direction of consciousness evolution. Is awareness developing towards some cosmic goal or attractor that draws all intelligence toward common insights and capabilities? Or does consciousness evolve in diverse directions, exploring all possible forms of awareness and understanding? If multiple civilizations have existed throughout Earth's history, their combined exploration of consciousness space might have covered far more territory than human intelligence has yet explored. Perhaps the most profound implication of the cosmic perspective is the possibility that consciousness is not merely an emergent property of complex matter, but a fundamental feature of reality itself. Some interpretations of quantum mechanics suggest that observation and measurement play essential roles in determining physical reality, implying a deep connection between consciousness and the basic structure of the universe. If consciousness is indeed fundamental rather than emergent, then its repeated appearance throughout cosmic history becomes not just probable, but inevitable. This view suggests that the universe is not just capable of producing consciousness, but is actively evolving toward greater self-awareness through the development of increasingly sophisticated forms of intelligence. From this perspective, every conscious being, whether human or potentially pre-human, contributes to the universe's ongoing project of self-understanding. Each mind that contemplates the cosmos adds to the total amount of awareness in the universe, advancing the cosmic project of consciousness evolution. The implications for human responsibility and purpose are profound. If we are participants in a cosmic evolution of consciousness that spans geological time and potentially includes previous terrestrial civilizations, then our choices and developments contribute not just to human welfare, but to the universe's overall trajectory toward greater awareness and understanding. Every scientific discovery, every philosophical insight, every expansion of compassion and wisdom advances this cosmic project. Yet this expanded perspective also suggests that human civilization, however significant it may seem to us, is part of a much larger pattern of consciousness evolution that extends far beyond our species and our current historical moment. If we are not the first intelligence on Earth, then we are part of a longer story of consciousness development that began long before human history and will likely continue long after our current form of civilization has passed away. This does not diminish the significance of human awareness, but rather places it in a more expansive context. We are neither the beginning nor the end of intelligence on Earth, but rather one movement in a cosmic symphony of consciousness that may include countless other voices, both past and future. Our unique contribution to this symphony lies not in being first or final, but in the particular perspective on existence that human consciousness provides. Our distinctive way of experiencing wonder, pursuing understanding, and creating meaning in a vast and mysterious universe. As you drift into the deepest states of rest and contemplation, consider that your consciousness at this moment is part of this cosmic evolution of awareness. Every thought you think, every moment of understanding you achieve, every act of compassion you perform contributes to the universe's ongoing project of becoming conscious of itself. Whether you are participating in humanity's first experiment with intelligence or the latest in a long series of such experiments, you are adding your unique voice to a conversation between mind and cosmos that may be one of the most fundamental processes in the evolution of reality itself. The cosmic perspective reminds us that we are temporary participants in something far greater than ourselves, yet our participation is nevertheless essential to the whole. Like notes in a vast musical composition, our individual consciousness contributes to harmonies and patterns that span scales of space and time far beyond our immediate perception. In recognizing our place in this cosmic symphony of awareness, we find not diminishment, but rather a profound sense of connection, purpose, and belonging that transcends the boundaries of species, planet, and even geological time itself. Whether we are the first intelligence on Earth or one of many, we are conscious participants in the universe's greatest adventure. The evolution of matter into mind, of cosmos into consciousness, of existence into awareness of its own infinite creative potential. In this adventure, every moment of consciousness is precious, every insight valuable, and every choice significant in ways that ripple through scales of time and space that challenge the very limits of imagination. This is the cosmic perspective that transforms our understanding of intelligence, consciousness, and our place in the magnificent, mysterious, ever-evolving universe that has given rise to the capacity for wonder, understanding, and love. Let's move to our last part of the documentary. We now arrive at the gentle conclusion of our journey through deep time, ancient mysteries, and cosmic possibilities. Here, in this final contemplation, we embrace the profound comfort that comes from dwelling within questions rather than demanding answers, and discover how the mystery of whether we are first or latest in Earth's experiments with consciousness offers its own form of peace and wisdom. As you settle into the deepest layers of restful awareness, let your mind drift through all the territories we have explored together. We began by grasping the almost incomprehensible vastness of geological time, where Earth's entire history becomes a single year, and human civilization occupies only the final seconds before midnight. We discovered how the Silurian Hypothesis reveals that even our most impressive technological achievements would vanish almost completely after just a few million years, erased by the patient processes of geology that constantly renew our planet's surface. We explored the tantalizing anomalies of the ancient world, monuments of impossible precision, technologies that seem displaced in time, and metallurgical secrets that took centuries to rediscover, each hinting at depths of knowledge and capability that challenge our assumptions about linear progress. Our investigation led us into the geological record itself, where we learned that preserving evidence across millions of years requires not just durable materials, but extraordinary circumstances of burial, protection, and chemical stability. The fossil record, sparse and fragmentary, even for biological remains, becomes almost impossibly challenging for technological artifacts. Yet we discovered that certain types of evidence, isotopic signatures, altered mineral distributions, large-scale chemical changes, might persist far longer than physical structures, waiting for analytical techniques sophisticated enough to detect their subtle presence. We contemplated the vast cycles of planetary habitability that create windows of opportunity for intelligence to emerge and flourish. From the sun's gradual brightening over billions of years to the ice ages that have punctuated the last few million years, from magnetic field reversals that alter cosmic radiation exposure to the complex interactions between atmospheric chemistry and climate stability, we found that Earth's capacity to support complex life varies dramatically over time. These cycles suggest that intelligence might emerge during particularly favorable periods, only to face environmental challenges that test its ability to adapt and survive. The Great Filter Hypothesis confronted us with one of the most sobering possibilities in cosmic philosophy: that intelligence may be common in the universe, but faces challenges so severe that most experiments with consciousness ultimately fail. Whether this filter lies behind us in the difficulties of emerging from primitive life, or ahead of us in the challenges of managing advanced technology without self-destruction, shapes our understanding of both cosmic loneliness and our own civilization's prospects. The archaeological record of human societies provides abundant evidence that even sophisticated civilizations can collapse suddenly when they exceed their environmental limits or fail to manage internal conflicts. We marveled at the sophisticated methods now being developed to search for evidence of ancient intelligence, from quantum sensors that can detect gravitational anomalies to artificial intelligence systems that identify patterns in vast data sets of geological and chemical information. These tools are bringing unprecedented sensitivity to the search for technological signatures in Earth's deep past, while simultaneously advancing our ability to detect signs of intelligence around other stars. The convergence of multiple advanced technologies creates possibilities for discovery that seemed like science fiction just decades ago. Throughout our exploration, the cosmic perspective has transformed every question we've considered. From the vastness of space and time emerges a view of consciousness not as an accident of recent evolution, but potentially as a fundamental feature of cosmic development, the universe's method of becoming aware of itself. If intelligence has emerged repeatedly throughout Earth's history, then awareness may be woven into the fabric of reality in ways we are only beginning to understand. With each experiment in consciousness contributing its unique perspective to an ongoing cosmic conversation. Now, as we rest in the gentle embrace of uncertainty and wonder, we discover that the question itself, whether we are first or latest, offers its own profound teachings about the nature of existence, meaning, and our relationship to the vast cosmos that surrounds us. The mystery invites us to embrace a form of cosmic humility that recognizes the limits of human knowledge while celebrating the remarkable fact that we can ask such questions at all. In a universe of billions of galaxies, each containing billions of stars, the emergence of minds capable of contemplating their own origins represents something extraordinary, regardless of whether those minds are first, latest, or somewhere in between. The comfort of mystery becomes particularly profound when we consider how much our sense of meaning and purpose depends not on having final answers, but on participating authentically in the ongoing process of inquiry and discovery. If we knew for certain that we were the first intelligence on Earth, we might feel the weight of cosmic loneliness, but also the pride of being pioneers. If we knew definitively that many civilizations had preceded us, we might feel part of a larger story, but also diminished by comparison to those who came before. Instead, dwelling within the uncertainty allows us to appreciate both possibilities while being defined by neither. This uncertainty also preserves the essential mystery that may be necessary for wonder and growth to continue. Perhaps the cosmos is structured in such a way that consciousness always finds itself poised between the known and unknown, between evidence and mystery, between understanding and wonder. The persistent gaps in the geological record, the ephemeral nature of technological signatures, and the vast scales of time involved may not be obstacles to knowledge, but rather features that maintain the conditions necessary for consciousness to continue expanding its understanding and appreciation of existence. The question of previous civilizations also illuminates the profound interconnectedness of all forms of consciousness across time. Whether we are first or latest, we participate in the same fundamental processes that have shaped the emergence of awareness throughout cosmic history. The atoms in our bodies have cycled through countless forms over billions of years, perhaps once part of other conscious beings who contemplated the same stars we see tonight. The evolutionary processes that gave rise to human intelligence operated according to the same principles that might have produced other forms of consciousness millions of years ago. In this deep material and energetic sense, we are connected to all awareness that has ever existed or ever will exist. This interconnectedness extends beyond the material to encompass the realm of ideas, insights, and understanding. Mathematical truths remain constant across cosmic time. The relationships that describe planetary orbits, the principles underlying chemistry and physics, the logical structures that enable complex reasoning. If previous civilizations existed, they discovered some of the same fundamental insights about reality that our scientists and philosophers continue to develop. In grappling with the basic questions of existence, consciousness, and cosmic purpose, we may be continuing conversations that began long before human history and will persist long after our current form of civilization transforms into something we cannot yet imagine. The potential cyclical nature of intelligence on Earth offers a unique form of cosmic hope and continuity. Unlike linear models of progress that depend on continuous advancement and preservation of knowledge, cyclical intelligence suggests that consciousness itself is resilient, capable of emerging repeatedly from the raw materials of evolution and planetary development. If civilizations rise and fall in geological cycles, each experiment with intelligence represents the universe's continued commitment to developing awareness and understanding. The collapse of individual civilizations becomes not a final ending, but rather a transition between different explorations of consciousness and its possibilities. This cyclical view also suggests that consciousness evolution may be far more robust and persistent than we typically assume. While individual civilizations may face existential challenges that test their survival, consciousness as a cosmic phenomenon may have persistence mechanisms that operate over much longer timescales. Each experiment with intelligence, successful or not, contributes to the overall development of consciousness in the cosmos. Failed civilizations are not wasted experiments, but rather explorations of consciousness space that inform the development of subsequent intelligences. The implications for our own civilization's purpose and responsibility become both more expansive and more gentle when viewed from this perspective. If we are participating in a longer story of consciousness evolution that spans geological time, then our specific achievements and failures take their place within a much larger pattern of development and discovery. This doesn't diminish the importance of our choices and actions, but rather places them within a context that transcends the immediate pressures and anxieties of our historical moment. Our responsibility becomes not to solve all problems or achieve final understanding, but to contribute authentically to the ongoing cosmic exploration of what consciousness can become and accomplish. Every act of genuine inquiry, every expansion of compassion and wisdom, every choice to create rather than destroy adds to the universe's accumulated experience with intelligence and awareness. Whether we are first or latest, we are uniquely positioned to contribute our own distinctive perspective to this cosmic conversation. The scientific search for evidence of previous civilizations, regardless of what it ultimately discovers, represents one of humanity's most noble endeavors. In developing the tools and methods to detect ancient intelligence, we advance our understanding of planetary history, geological processes, and the preservation of information across vast timescales. We learn to read the subtle messages written in stone and sediment, expanding our literacy in the languages that planets use to record their own experiences. These skills serve us well, whether we discover evidence of previous civilizations or confirm that we are indeed the first. The search also embodies some of the highest values of conscious beings: curiosity, humility, persistence, and respect for evidence over assumption. In approaching such profound questions with scientific rigor, rather than wishful thinking or dogmatic certainty, we demonstrate the kind of intellectual integrity that may be essential for any civilization's long-term success. The methods we develop, the standards we maintain, and the wisdom we cultivate in this search become part of our legacy to whatever forms of consciousness may follow us. Perhaps most importantly, the inquiry itself transforms our understanding of time, existence, and our place in the cosmic story. Whether we ultimately discover evidence of previous civilizations or not, we have already discovered that consciousness exists within a context far vaster and more mysterious than previous generations imagined. We have learned to see ourselves as temporary expressions of cosmic creativity, participants in an ongoing exploration of what matter and energy can become when organized into forms capable of wonder, understanding, and love. The peaceful acceptance of uncertainty allows us to embrace our role as conscious explorers in a universe that may be far more populated with intelligence than we yet realize, or may be testing consciousness for the first time through our particular experiment with awareness. Either possibility fills our existence with meaning and purpose that transcends the need for final answers or ultimate certainty. As you drift now toward the deepest rest, carry with you the gentle wisdom that comes from dwelling comfortably within great questions rather than demanding premature answers. Whether humanity represents Earth's first experiment with consciousness or its latest iteration, we are here now, aware and wondering, capable of contemplating mysteries that span billions of years and encompass the fundamental nature of existence itself. This capacity for wonder, this ability to ask questions that stretch beyond the boundaries of immediate experience, this willingness to search for truth, even when it remains tantalizingly beyond our grasp, these may be among the most remarkable achievements of consciousness in the cosmos. Rest peacefully in the knowledge that your awareness at this moment is part of something magnificent and ongoing, a cosmic process of self-discovery that began with the first stirrings of consciousness and will continue as long as aware beings exist to wonder about their origins and contemplate their place in the vast, mysterious, ever-evolving universe. Whether you are among the first conscious beings to ask these questions or one of countless intelligences who have pondered the same mysteries across geological time, your participation in this cosmic conversation is unique, valuable, and irreplaceable. The universe has organized some of its matter and energy into the form of your consciousness so that it might experience wonder, pursue understanding, and perhaps glimpse something of the profound beauty and mystery that underlies all existence. In this role, as the universe's way of knowing itself, you join a community of awareness that may span far more of space and time than we yet understand. Whether this community includes only human consciousness or encompasses countless other experiments with intelligence, its essence remains the same: the remarkable emergence of mind from matter, of awareness from complexity, of consciousness from the creative depths of an inexhaustible cosmos. Sleep well, fellow traveler, in the vast journey of cosmic awakening. Tomorrow will bring new questions, new possibilities for discovery, and new opportunities to participate in the universe's ongoing exploration of its own infinite creative potential. Tonight, rest in the comfort of mystery, the peace of uncertainty, and the profound satisfaction that comes from being conscious participants in the greatest adventure of all, the evolution of a universe toward ever greater awareness, understanding, and appreciation of the magnificent mystery of its own existence.